Part two of complex exposure settings, the rank and sum cheat, shortcut, whatever you want to call it. All right, so here's problem two. Which factors result in the lowest optical density? We've got 5 conditions: MA milliseconds, KVPs, speeds, grids, and distances. Oh boy. All right, so step 1, calculate the mass. 500 MA times 500 milliseconds divided by 1,000 milliseconds per second gives me 250 mass, right? I want milliamp seconds, not milliamp milliseconds. All right, so calculate the mass for all 5 conditions. We're off and running. Rank the masses from the darkest to the lightest. So 250 is the biggest one, 125 is the second biggest one, 50 is the third, 20 is the fourth, 10 is the fifth. Okay? All right, next, let's rank the speeds. All right, I did that next. So 800 speed means it's most sensitive. So that means it's going to get the darkest with the least density. Then 600, then 300, then 200, then 100. Faster speed, faster sensitivity goes from white to black with very little dose. Okay, the grids. No grid gets the most onto the detector. Then the thin grid, the thinner grid, the thinnest grid, the tallest, thinnest grid, whatever. All right, so the grids go, they were in order. I was lazy. All right, and then let's rank our distances from the closest, that would be the most intense, to the second closest, third closest, fourth closest, fifth closest. Okay? So we rank all our factors, and then we sum them up. Row A is 5 plus 1 plus 3 plus 1, 10. Row B is 13, C is 14, D is 11, E is 12. Okay, so the lowest number, A, is going to give us the highest optical density. Let's see. They're all ranked by density, so condition C is the highest number, so that's going to be the lowest density, right? C was our lowest ranked one, so it got the highest value because we ranked them from most dense to least dense, and it is our lowest density. Okay, and is it far away from others? It's kind of close to B, but it's pretty far out from the other two. All right, so let's do it the real way. The real way starts out the same way. We calculate the masses. Then we say, all right, let's pick a condition. I'll pick 93 kVp and scale all the masses as if they were the equivalent mass. The equivalent mass that would be used at 93 to result in the same optical density. So 81 at 125, 81 15% gets me to 93. The same optical density as 81 and 125 would be 93 at half of 125. So I cut that number in half, 62.5. All right, my 70s have to take two 15% steps, so the mass has to cut in half and cut in half again. So 50 divided by 4. This 81 cuts in half. It only did one step. And the 60 takes 3 steps. 60 to 70, 70 to 81, and 81 to 93. In each step, I have to cut the mass in half. So the result is half times a half times a half is 1/8. 250 divided by 8. So these are the masses to give the same optical density as these conditions if they were at 93 kVp. Then we've got to scale them for speed. So pick a speed. We'll pick 100. So 31.3 at 93 kVp at 100 speed is the same. Okay, here's 200. So if it's a 200 speed, it's going to get darker quicker. So 62.5 mass at 200 speed is the same as 125 mass at 100 speed. It's the ratio of the speeds, using that to scale my mass. This 800 speed one is going to be, 8 times more sensitive. So 5 mass at 800 speed would be like the same as 40 mass at 100 speed. Okay? So we scaled our masses. Now we scale for grid factors. So the no grid one, move it right along, 31.3. The 4-to-1 grid relative to a no grid, well, you're going to have twice as much cutoff, or you'll need twice as much intensity. So the 60 gets cut in half. A 6-to-1 grid factors are 3. A 3-to-1, a 3 grid factor versus the 1 means I'll have to cut it by a third. The 8-to-1 is a grid factor 4. So 75 at an 8-to-1 is like a quarter of that shot with no grid. And the 12-to-1 is a 5 grid factor, so we're doing a fifth of that. Okay? Now we're going to scale them for distances. We'll make it all look like it is at 80 inches. So if I was at 90 inches with 30 mass, that would be the same optical density on my detector as 23.7 mass at 80, right? I go from 90 inches to 80 inches, so my mass scales down by 80 over 90 squared. So you're going to use the ratio of the distances squared to scale your mass to figure out what would be the mass to result in the same optical density at 80 as the mass given the mass and the distance given. All right, so now you're done. You can see condition C has the 22 mass, equivalent mass. If C was done with no grid at 80 inches at 100 speed with a 93 kVp, it would give us an optical density as if it was 22 mass. And that is the lowest mass in this group, so that would be our lowest optical density. Again, if we go back and look at our factors, let's put them right up here. That 14 saying the ranked worst against optical density, meaning the lowest optical density, would have pointed at answer C as well. So, I don't know what to tell you. It's good to do it both ways. Maybe you do the rank and sum method first, and then you say, oh, I really got to decide between condition C and D, and then you only scale condition C and D for KVP, speed, grid, and distance. It could save you some math, or you could do these problems the pure way and then the rank and sum and see if they jive, or you could rank and sum them and move on and come back to them at the end of the test, or you can rank them, sum them, and then say, oh, I really only have to fight it out between condition A and C. All right, I hope that helps you. This is XRayBob signing out. Oh, where do we stop this thing? Hey.